Get started. So hi everyone. Excuse me, wait. Okay. Hi everyone. Welcome to this month's MMMRN webinar. So today we have an amazing scientist and very accomplished scientist, in fact, with us, Dr. Kayla Nguyen. And today she will be sharing her research on new direct electron imaging techniques for quantum materials. So before she starts her talk, I want to introduce her a little bit. So Kayla is currently an Illinois Distinguished Postdoctoral Researcher at the University of Illinois Urbana-Champaign. She's also a 2020 Laureate for Women in Science Postdoctoral Fellow. Kayla received her PhD from Cornell University, and there she was the co-inventor of the electron microscopy pixel array detector. And for that, she won the Lemelson MIT Student Prize Award. She also earned various other accolades, including the Japan Times One of Five Promising Asian Researchers and the Microscopy Today Innovation Awards. Kayla now focuses her time on developing new electron microscopy techniques with an emphasis on pushing the boundaries for the resolution and for the resolution of the magnetic structures and the organic molecules. In addition to her role as a scientist, she also is extremely passionate about building a more diverse and inclusive environment for women in STEM field. She also has been involved in building accessible pathways for girls and young women to enter the science, technology, engineering, and mathematics fields. So without further ado, I would like to welcome Kayla, and Kayla, you can proceed now.
Okay. Thank you so much, Sharia, for the nice introduction. And so I'm going to see if I can pin my video. There we go. Perfect. All right. So my talk is kind of long, so I'm just going to go straight into it. But thank you for inviting me to give this seminar. And it's a great honor, so I'm going to start. All right, so the title of my talk is called New Direct Electron Imaging Techniques for Quantum Materials. So if you look at this image here, what you see are these vortices. So they're actually polarization vortices that come about when you take a layer of lead titanate and strontium titanate and you stack them on top of each other. And so what we can do with these new quantum materials is we can probe their really interesting physics with electron microscopy. And one of the things that we can do is get back information related to the change in angular momentum of these ferroelectric materials. All right, cool. So the technique that I utilize in my research is called scanning transmission electron microscopy, STEM for short. So what happens in a scanning electron microscope or a scanning transmission electron microscope is you have an electron beam that gets focuses down to a spot that's about an angstrom wide with electromagnetic lenses. And so you take your electron beam and you scan it across the sample. And at each scan position, the scattered electron gets collected into this angular dark field detector. And you can integrate that signal up to form really nice atomic resolution images. And if you look at these images here, what you see are really dark atoms and really bright atoms. So materials that have a bigger Z element, something heavier like lead or bismuth, will show us brighter because they scatter more at higher angles. Whereas lighter materials, in this case, maybe strontium or titanium, show us darker because they don't scatter as high of angles as an angular dark field detector. I mean, as the heavier Z elements. And so that's really cool because we can image atoms. However, the scatter electron beam gives us more information than just the structure. We can use it to image magnetic fields or electric fields and more properties beyond the structure. And so the question is there a way for us to do this, or is there a way for us to design our experiment to do that? And so how can we extract this information? So one of the ways we can do it is utilize a technique called 4-dimensional scanning transmission electron microscopy, 4D STEM for short. So now what we have is, instead of having an angular dark field detector that collects scattered electrons and integrated it up to get these really nice atomic resolution images, what we can do is we can replace that with a direct electron detector, in this case, the electron microscope pixel ray detector, MPAD. And so for each scan position of the electron beam, we're collecting the full electron diffraction pattern. And so now what we can do is we can make virtual masks, for example, the same size as an angular dark field detector, and reconstruct our angular dark field image, or we can choose different regions of the diffraction pattern where we can integrate that signal up, for example, to reconstruct an angular bright field image. Or we can use the whole entire diffraction pattern and reconstruct the center of mass and the integrated center of mass image, where we can look at not just heavier atoms, but lighter atoms such as oxygen in the same image. So by being able to collect the full electron diffraction pattern, we can get more than one type of signal. And this is really cool because now we have all this scattered beam information. So a little bit more about the Mpad detector. What makes it a really powerful detector is that it can read out the pixels in parallel. So you're framing at 0.8 milliseconds per frame. Typical CCD detectors for electron microscopy frame about 10 to 100 milliseconds. It has single electron sensitivity, so you can get single electrons detected, and the noise is 1 in 140 electrons. And then what's the really big thing about this detector is that it has a very large dynamic range. What this means is you can detect 1 electron or 1,000,000 electrons without saturating the diffraction pattern. And typical detectors can go up to maybe 25 or 100 electrons, but it can't have that high dynamic range that we have. So if you look at the diffraction pattern here, what you've noticed is that you have a very bright spot in the center. This is what we called our bright field disk. And this is about tens or thousands of electrons. And here at this higher scattered angle, where we call the Kikuchi bands, this is only a handful of electrons. And so now, because we can record every electron that passes through the sample at every probe position, we can get the full scattered beam information in a way that we haven't been able to before. And so this detector was something that I developed with a group of scientists during my PhD. And during my PhD, it was actually exclusively licensed to Thermo Fisher Scientific. It's a multi-billion-dollar company, and it's now sold around the world. We have one at UIUC, the University of Illinois Urbana-Champaign. There is one at University of Michigan, a couple at Argonne National Lab, one at the Weizmann Institute in Israel, and then Monash University. So it's floating around. And so here is where the Mpad sits on our aberration corrected microscope at Cornell. And here's me holding it. This is our digital control unit back here. And this is the camera that operates everything. All right, great. So why is it so important for us to keep on developing new detectors or new microscopes to get this information? If we're at the limit of imaging atoms, why is it so important? So this is a plot of resolution in microscope, and it's actually a historical plot. So as we increase resolution, we can see things about the world that we haven't been able to see before. For example, with the invention of the light microscope, we're able to look at skin cells. With the invention of better optical lenses, we can look at bacteria. And then within the invention of the electron microscope, we're now looking at viruses, which are very important for what's going on right now, especially with the pandemic. Better lenses, proteins, molecules, atoms, and then this is where the Mpad sits. So now, instead of having to make bigger microscopes that have better lenses, what we can use is we can use information collected in our detector to get an idea and a sense of resolution beyond what we had before. And so with the Mpad, we can use it to push the limits of resolution. And this work actually gave us the highest resolution in the world and the Guinness World Record for that resolution. So not only can we utilize new detectors and new techniques to look at things in a way that we haven't been able to before, we can also use it to study physical properties of material systems. And in my talk today, I'm going to be talking about how we can use these new detectors, information from the scattered electron beam, to image magnetic materials. And then the second part of my talk, I'm going to talk about how we can use that to look for new physics of topological ferroelectrics. All right, so here is the beginning of my talk for magnetic imaging. Oh, if there's any question, feel free to stop me and I can answer your question for you, or just let me know. Maybe there was a question, or maybe there was some.
No, I think there wasn't a question. It's just someone unmuting by.
Okay. All right. Okay.
All kinds of things happen in Zoom.
Oh yeah. No problem. Yeah. So if there is a question, just let me know, or I can just go on with my talk. I made this talk to cater to more of the audience, so let me know how it goes, but I will just go along with my talk. Great. So the first part of my talk is how we can image magnetism in the electron microscope and how we can disentangle, for example, grain information from magnetic structures and get back the signal that we want to get. All right. So why do we want to image magnetism? So magnetism is really important because we see it every day of our lives in the devices that we use, for example, our earbuds, our phones, and it's also used in navigation systems. Magnetism is also really important for scientists and people because data storage is a big issue. And one example of a way to solve this problem is to look at magnetic skyrmions because they represent the smallest spin textures in magnetic thin films. Secondly, there are these new and emergent topological magnetic materials, for example, anti-skyrmions, which we can utilize in the future for data storage or other types of computating technologies. And so in order for us to understand how to use these materials, we need to learn how to characterize them.
So sorry, excuse me. So please, everyone, don't unmute yourself by mistake. Sorry about that. Yeah, Kayla, you can go ahead.
It's fine. And so we can push for more details in emerging magnetic structures. All right. So then the question is, how do you actually image magnetism, or how does it work in the electron microscope? So when you're taking your electron beam in the electron microscope, you need to focus it down to electromagnetic lenses. And these electromagnetic lenses are controlled by electromagnetic fields. So there is a field in the microscope. So one field in particular that is really strong and next to the sample is the objective lens field. So this is the lens that focuses the beam. And so this lens actually applies a field that is 2 Tesla to your magnetic sample. And because you're applying a field that is 2 Tesla, all the spins of your sample gets aligned to the field of the microscope. This is not what you want. What you want is to image the intrinsic field of the sample. And so what you have to do is you have to turn off the objective lens. And so now you're looking at the intrinsic field of your sample. The issue with this is that with the objective lens on, you have a very focused probe that gives you 1 angstrom or 0.1 nanometer resolution. By turning off the objective lens, your resolution then becomes 2 to 4 nanometers. But that's fine because the magnetic structures that we're looking at are about 50 nanometers. Okay, so that's one thing you need to do is make sure you turn off your objective lens so that you're not applying a field to the sample and the spins of your sample are not aligned to the field of the microscope. The second part is how do you actually look at or image fields with electrons? And so then we go back to the Lorentz force law, where we have F equals Q dot E plus V cross V. And so what happens is that your electron, as it scatters through a magnetic sample, gets deflected by the local magnetic field. And this deflection we can actually calculate. In an electron microscope, a typical magnetic deflection is about 18 microradians for a 10 nanometer thick film iron if we're using an electron beam that images at 100 kiloelectron volts. So this deflection is actually quite small relative to our Bragg angle, which is about 4 milliradians. So we're looking for a very small deflection compared to a crystallographic deflection. And so what we can do is we can take our electron beam, put in a magnetic sample, and take our diffraction pattern, and from that try to get back information related to the magnetic field. And so within the diffraction pattern, we can calculate the center of mass. So visually, what this means is that these are electron diffraction patterns at position 1 and position 2. Electron diffraction patterns are basically the intensity of the wave function. And what we want to do is measure the change in momentum. So this equation is basically saying that if we take two positions, for example, position 1 and position 2, and we subtract them from each other or look at the average change in momentum, then we should get a deflection related to the local magnetic field. And here, what you can see is that as we subtract these two diffraction patterns, we get changes. It goes from red to blue, or it goes from top to bottom, depending on what you choose your direction, of how the electron beam is deflected by the local magnetic field. And so this deflection, this change in momentum, can be directly related back to the Ehrenfest theorem, and we can get back information related to the magnetic field. And so we can directly measure the electromagnetic field using this technique in our electron microscope. And so one of the questions that people typically ask me is, what is the smallest field that you can detect in an electron microscope? And so there's two ways to answer this question. The first way is to look at the analytical model. So if your deflection is beta, then there are two variables that control the size of your deflection. And what we want is we want beta to be very, very small because we want to detect very, very sensitive field. And so these two components are alpha, which is the semi-convergence angle of the electron beam. In other words, the numerical aperture, and N, which is the number, is the electron dose. So from this, it's very obvious that with more electron dose, you can detect sensitive fields. Alpha is very interesting. So we're alpha limited because we're turning off the objective lens. And so alpha is on the order of a couple of hundreds of microradians. And so for a spatial resolution of 4 to 5 nanometers, what we can see is that we can detect millitesla fields in our numerical model. Okay, great. So let's just put our sample into the electron microscope, perform our 4D STEM technique. What should we get? So if we took a sample, for example, single crystal of B20 iron germanium, they form skyrmions intrinsically. And we look at the deflection in X and Y because we have a diffraction pattern. We can look at that change in momentum. And then we can take that magnitude of the signal and we get back information related to the skyrmions. And so this is the shape of the skyrmion that we get from our technique. And so if you take a line profile within the magnetic field image in the Y direction, and we fit it to a curve, what we get is we get a root mean squared of 3.6 millitesla. What this means is that we can detect very sensitive fields with the electron microscope. And this skyrmion is on the order of about 50 nanometers. So we can also look at nanoscale structures within our electron microscope as well. So how does our technique compare to the traditional techniques using a CCD camera in the electron microscope. So what people typically do in electron microscopy is that they take a CCD camera and they cut it up into quadrants, for example, top and bottom or left and right. And because the CCD camera can only detect a handful of electrons or can only detect up to 25 electrons, we can still see information related to the skyrmion, but it doesn't have that much dynamic range. With the Mpad, with these new detectors, we do get more information than what we had before. And so dynamic range matters a lot. Okay, so that's really cool. But the next part of my presentation, I'm going to talk about why it also matters, especially when you don't have a perfect single crystal, but when you have grainy structures. And so one of the ways that we can do our imaging is that we can do it in the presence of non-perfect crystals, not single crystals. So if we take a layer of our B20 iron germanium and we sputter it on top of a silicon film, what happens is that it intrinsically forms these polycrystalline grains. And so what we want to know is how can we extract information from the grain and disentangle it from our magnetic field. So we look at the diffraction pattern here. What we see is if we take only information transfer from inside of the bright field disk, we get a redistribution of intensity within the disk that gives us back our grain structure. However, if we take our entire diffraction pattern, we know that in the electron microscope, the electron beam gets deflected by the local magnetic field. And so what it does in diffraction space is that it shifts the whole entire disk. And so from that, these lines here represents the ground state of a skyrmion, these helical phases. For skyrmion structures, you have to turn on a magnetic field for it to actually curl to form skyrmions from the Diffraction-Morier interactions. So within the ground state, what we see are these helical phases that we can extract from our magnetic imaging. So now there's two ways to look at our image. One way is to look at just the grain structure, and the other way is to look at the magnetic shifts. And so here, what we can do is now that we have two separate ways to look at magnetism and grain contrast, we can separate magnetic and grain contrast in polycrystalline iron germanium on silicon and get back information related to the magnetic fields. And this is really important because most devices are not grown as single crystals, but do correlate to sputtered material because that's a manufacturing problem. And so for us, it's important to study real devices that are sputtered and not these perfect single crystals. All right, so then what happens in our material structure when we do form these skyrmions? So now, instead of having your ground state, which are these helical phases, so these squiggly lines, you apply a magnetic field, a small magnetic field to your material. And because of the Diffraction-Morier interaction, your helical phases starts curling. And when it starts curling, what you do is you form these magnetic skyrmions. And so if you look at this magnetic skyrmion structure, you can see that the top grain here has skyrmions that are rotating counterclockwise. The bottom grain here has a skyrmion structure rotating clockwise. So now what is going on with the sample? Why are we getting two different regions of different rotation of the skyrmion, even though we're applying the same field to the sample? So what we do is we go back to our traditional imaging of the grain structure, and we realize that these are two twin grain boundaries or domains. And then at atomic resolution, what we find is that the top grain has a right-handed crystal chirality, and the bottom grain has a left-handed crystal chirality. We do another check where we look at the diffraction pattern, and within the diffraction pattern, you can see that we get very thin bands on the left side and a wider band on the right side. The opposite is true for the bottom image. We get the wider band on the left side and the thinner band on the right side. So what we find is that skyrmion vorticity, or the curl of the skyrmion is aligned with the crystal chirality. So how do we prove that this is also true? What we do is we go back to micromagnetic simulations. So we take a bunch of grains and we randomly added different crystal chiralities to the grains. And then we also added different signs of the Diffraction-Pattern interaction within this grain within this material as well. So we have it under different field conditions. And what we find is that within the grain boundaries here, because these crystals have different crystal chirality in our simulations, we find that this grain is rotating counterclockwise, and this grain this grain here is rotating clockwise, and the bottom grain here is rotating counterclockwise. So simulation supports our results and shows that the sign of the DMI, or the Diffraction-Pattern interaction, is aligned with the crystal chirality. So in summary, what we can do is we can image magnetic textures of B20 iron germanium. We can separate magnetic and grain contrast from the polycrystalline structure. We find that skyrmion vortices rotation change between grains of opposite crystal chirality, and magnetic simulations show that the DMI is aligned with the crystal. So magnetic simulations support our results. So finally, this provides insight for miniaturization of real devices based on magnetism. And you can find this result. It's published this year in March in Physical Review to Apply if you're really interested in reading the paper. Okay, cool. So I think right now it's about 25 minutes. So I think that I'm going pretty fast. So I'll just slow down a little bit when I go to my next section. So the next section of my talk is going to be on new physics of topological ferroelectrics. And so part of this work was published in 2019. The second part of this work is on arXiv. And I'm going to start with talking about actually orbital momentum. I kind of switched it up for the audience. And then I'm going to go into how we can image polarization in the electron microscope. And finally, if there's time, how we can use this to solve for three-dimensional chirality. All right. So when you think of orbital angular momentum, you first think about linear momentum. So in linear momentum, objects can move in a straight line. For orbital momentum, objects can also move in a circle. So what is orbital momentum? It's basically a way to look at objects moving through and moving in circles. For the electron microscope, orbital momentum for electrons is complicated. But what you need to know is that it's important for understanding certain phenomena. So if you take an electron microscope, what you typically have are these plane waves. And if you put it through a spiral faceplate, you can torque the electron beam, and now it has some orbital momentum. So if you take the plane wave and pass it through a filter, for example, this faceplate, the plane wave picks up orbital momentum and becomes a spiral type wave. And what orbital momentum is important for is important for memory, sensors, and communication. So now if we think about imaging orbital momentum in the electron microscope, we can think about taking an electron, putting it through something, and getting torque from that information. So instead of having a spiral faceplate, what if we have a topological ferroelectric? So for example, polarization vortices in lead titanate, strine titanate. This is a sample that has been really interesting and has gained a lot of interest recently, where you take a layer of lead titanate, particularly 10 to 12 unit cells of lead titanate, and stack it on top of 10 to 12 unit cells of strine titanate. because of the energetics of the system, it forms these polarization vortex. So now what we can do is we can take a plane wave of electrons, so basically a regular electron beam, and scatter it off of one of these lead titanate, strontium titanate polarization material and see what we get. So in general, instead of a spiral phase plate, we can replace it with a ferroelectric polarization vortex. And what we want to know is that how does this vortex structure torque the electron beam? For example, if we want to use it for real devices, how are we going to utilize this polarization mechanism in a real device? And the one way to do it is to characterize that with the electron beam. Okay, so this part of the talk will have one equation, which I would put here first, where it's a technique that we developed to calculate torque transfer in our electron microscope. But I will also have a schematic to show what we're actually doing. So imagine your electron beam is a small boat or a small float in a spiral. And so what we can do is we can take our electron beam and watch it spiral within these polarization vortex, where we see that at the center of the spiral, we get the maximum signal. So when we have an electron beam that is smaller than the sample, orbital momentum can map the vorticity, i.e. the beam is rotated by the curl of the vector field. And for ferroelectrics, it's the polarization field here, which is del cross P. So if we want to look and reconstruct polarization and orbital momentum from our sample, then we need to take the electron beam and we need to figure out how it curls around this polarization vortex. And it's simply by just knowing our polarization field and applying this torque transfer equation. All right, so what we're going to do is we're going to utilize our 4-dimensional scanning transmission electron microscopy technique, or 4D STEM, to do this experiment. All right, so there are questions in the chat. For example, the first question is, are these polarizers and some kind of electron polarizer? So no, it's not a polarizer. It's just simply a sample that has polarization vortices. So these polarization vortices, when I mean polarization, I meant electric dipoles. So the electric dipoles cause these cause your atomic unit cell to reorient it so that when you look at the change and displacement of your unit cell, it actually forms these polarization vortex. And so technically what it is it's an intrinsic polarization vortex structure in a ferroelectric material. And so what we want to learn is how does it change your electron beam and how does it torque your electron beam? Hopefully that answer is satisfying. All right, great. So what we're gonna do first to start, okay, great, thanks. So what we're gonna do first in our experiment is we're going to perform 4D STEM. So we take our data and we record our electron diffraction pattern. And from our electron diffraction pattern, we can get images that look like this. So what you see here are, instead of using a probe that is about 1 angstrom, we're actually going to make our probe quite large. We're going to make it about 7 angstroms, where, and there's a reason for that, which I will explain in the next slide. But we're going to use a quite large beam, and our diffraction disk, when we use a quite large beam, instead of having it overlap where it stacks perfectly next to each other, it's going to be non-overlapping. And the reason for this is now we can actually probe different diffraction disks. And so what we're going to do is we're going to calculate the center of mass of different diffraction disks, because what we've noticed in our diffraction pattern is that depending on the direction of the polarization vortex, our diffraction pattern also changes. So for example, this top part of our diffraction pattern shows that the intensity is going from left to right. the right part F goes from top to bottom. The G part here goes from right to left, and the D part goes from bottom to top. So if we track the change in our non-overlapping diffraction disk, we can also map out the polarization vortex this way. And so how do we get back information related to polarization vortices? So the first part is that we're going to start off with Cattell, Introduction to Solid State Physics. All right, so what Cattell tells us is that ferroelectrics they have macroscopic fields, which means that it's related to the displacement field and also the polarization field. And so because ferroelectrics are macroscopic fields, by definition, it is the electric field equals to the average field over the volume of the crystal that contains the lattice point R. Systematically, what this means is that if you have an atomic size probe, for example, an electron probe that is 1 angstrom, that is smaller than the unit cell of your material. And so this is only the microscopic field. So if you're looking at if you're looking using an angstrom size probe, 1 angstrom, then you're only looking at this nuclear field. So if you're imaging atoms, you're not actually looking at ferroelectric fields, because ferroelectric fields are macroscopic field. So what we have to do as scientists, as electron microscopists, instead of looking at individual atoms, we need to make our probe larger. So the unit cell size of strontium titanate and lead titanate is around 4 angstroms. And so for us, what we need to do is we need to make our probe about 5 to 7 angstroms so that we're averaging over the unit cell. So we're getting this macroscopic ferroelectric field. So this equation tells us that in order to get back this ferroelectric field, we need to use a large probe that averages over the unit cell size. And so instead of having an atomic size probe, we need a bigger probe where we can average over the unit cell and we can get a larger field view. So now what we can see is that we can image ferroelectric fields if we have a macroscopic probe. So we're not going to look at individual atoms. Instead, our images are going to be showing intensity related to only something that is on the resolution of 5 to 7 angstroms. So we won't see atoms in our images, but that's fine. So another thing about ferroelectric fields is that there's a relation between the local displacement field or electric field and a relation between the polarization field. And so this is something we can actually extract individually in our diffraction pattern. So if you look at, when you think about polarization in terms of diffraction, in order to get polarization information, you need to break symmetry. And so you need to look at pairs of the diffraction disks in order to get back information related to polarization. However, if you only want to look at the electric field, then what you can do is that you can look at the center disk, because that shifts, because there is no polarization information in the center disk because there are no conjugate pairs with the center disk. It's just a 0-0 disk and that's it. And so if we look at the change in center of mass, where we mass all of these other disks and only look at the center disk, what we see is we get information back related to the electric field. And so what we find is that our electric field is pretty flat. We're not getting a lot of structure in it. So that means that there's not much going on with the electric field. Now, if we take, for example, the 200 disk, which is the distance of titanium relative to lead, we can get back information related to polarization. And that is because polarization requires conjugate pairs and conjugate pairs that break asymmetry. And if you look at the 020 disk, what you can see is that that also breaks symmetry. And so now you have information related to polarization in the X and in the Y direction. And so now you have these two vector components, a polarization, and you take these vector components in X and Y, a polarization, and now what you can do is you can reconstruct these vector plots and get back your information related to the polarization vortices simply by looking at the asymmetry of your conjugate pairs of seabed disks, diffraction disks. All right, so now that you have your polarization information, how do you get back torque transfer? And so because the beam is rotated by the curl of the vector field, all you need to do is take the curl of your polarization field, which you know here, and then you can apply the torque transfer technique or the equation that I showed you in one of the beginning slides. And from that, you get back information related to angular momentum or angular momentum of your sample. Great. Okay, so now it's about 39 minutes. Sharia, let me know if you want me to summarize, or I have one more section left.
I think you can summarize, and also, like, how long is the last section?
I think it's a good like 15 minutes. So yeah.
It's fine. I think you can go ahead and summarize and then do the last section as well.
Oh, well, I was, so the last section is also a polarization. So do you want me to summarize my talk or summarize or go, or yeah, sorry.
I think the way you plan first, like you can summarize this.
Great.
Yeah.
So just summarize, just end my talk. Okay, great. Right? Okay, double checking. Yeah, okay, great. Sorry. Okay,
so you're not gonna go through last section?
Well, the last section is on chirality and how I was able to extract chirality. I can go through it really quickly and then summarize, if that's okay.
I think let's do that. Yeah, because I think I really want to hear your last section as well.
Yeah, sure. Okay, so I'm gonna go into my last section. This might be kind of fast, disclaimer, so feel free to ask questions. I know there's this question in the chat, but I'm just gonna leave it for the end just because I just want to finish the rest of my talk, if that's okay. Okay, so now that we have a way to look at torque transfer, one of my professors asked me, is there a way for us to extract chirality in our sample? And so one of the first questions is our sample two-dimensionally chiral or three-dimensionally chiral? So to answer the question whether or not it's two-dimensionally chiral is quite easy. Because you have these polarization vortices, one is firing counterclockwise and one is firing clockwise, if you take them on top of each other and rotate them or translate them, no matter what you do, you can't actually put them directly on top of each other. They're kind of like your hands, where no matter how you translate your hands, they're never going to stack perfectly on top of each other. And so we know that our sample is two-dimensionally chiral. Now the question is it three-dimensionally chiral? And so what we need to do is we need to make a new sample, and instead of looking at in this direction where we're looking at down the 0, 1, 0 direction, we need to look down the 0, 0, 1 direction to see how that structure looks like. And so we need to look at sideways. And so why is chirality important? Well, chirality is important because what we can do is we can learn how to tune our polarization structures with different chiralities of light. For example, different types of polarized light, left-handed or right-handed. And there are new emerging ferroelectric skyrmion structures that also have chirality. So it's important for us to utilize chirality and understand how different or how chiral our sample is. So if we're looking at down the three-dimensional structure for chirality down the 0, 0, 1 zone axis, there are two different structures that we can get. So if you take this structure here, and then you rotate 90 degrees, it's gonna lie, horizontally. So just imagine this rotate 90 degrees. So if our sample is two-dimensionally chiral, then what we should get are these flux closures, these loops within this beam direction. Now, if our sample is three-dimensionally chiral, then instead of having flux closures, we should get a spiral. And so three-dimensionally chiral structure means that we should get a signal for Px and Py if we're looking down the 0, 0, 1 zone axis. And so what we see in our sample is that we do get information down the 0, 0, 1 direction, where we get chirality in P. And so we find out that our sample is three-dimensionally chiral. So then the question becomes, is our sample right-handed or left-handedly chiral? And so to solve that question, we go back to DFT simulation, where we get DFT simulations of these polarization structures, and we can just sum it up in the projected direction. And we find out that if our sample is right-handedly chiral, PX and PY lie directly on top of each other. If it's left-handed chiral, they're 180 degrees out of phase. And so if we can overlay our two PX and PY images on top of each other, what we find is that there are regions of the sample that are right-handedly chiral, and there are regions of our sample that are left-handedly chiral. And if you go back to our PX image, we can see that they form these domains within our sample down the 001 direction, where there are domains that are left-handedly chiral and right-handedly chiral. All right, so this is my, so in summary, we can look at electric and polarization fields with one data set. We develop a phase-sensitive technique to look at change in angular momentum, LZ. We can solve for three-dimensional chirality, and we can find the domains of left-handed and right-handed chirality. So the Mpad gives us information about the four-dimensional space without saturation. We can use that to uncover natural order parameters of new quantum materials, and we can understand and utilize these natural phenomena. And so here are just a couple of things that we can do with these new detectors and four-dimensional STEM. But there's so much more, because there's so much more information that we can extract from that. And so my hope is that people utilize this technique more and study really cool and interesting materials. And so this is my acknowledgement slide. So I thank Sharia very much for inviting me, and I can open up the floor for questions.
Hey, Kayla, thank you so much. That was an amazing talk. Amazing talk.
It was a lot. I'm so sorry.
Yeah, it's a lot, but I think it went fine. It's very interesting. So yeah, we will open the floor for questions. So if you guys have any question, you can unmute yourself and ask it, or if you want to chat, use the chat box, that's also fine. So before I leave it for the audience, I kind of, oh, okay. There is a raised hand by Riyaj. So yeah, Riyaj, if you want to unmute yourself and ask the question, that would be great.
Hello. I really enjoyed your talk because my undergraduate thesis was kind of on microscopy. So it kind of sparked inside, it kind of sparked something inside. So I have a few questions regarding. First is you said that when you're modeling the magnetic field, you shifted the system and then you take the difference, if I'm not wrong.
So which slide are you talking about?
When you're mapping the magnetic field.
Yes. This slide right here.
Yes, this one. So when you are mapping the magnetic field, you said that you just shifted the system and then calculated the differences, right? So my question was that magnetic field is the vector potential that we know. So vector potential is mainly a function of velocity, and the scalar potential is mainly a function of distance. So how are you sure that it is mainly that it is it is magnetic field, not the electrostatic field?
Right. So this is just a visual on how we're just to give you an idea of how magnetic field changes in the electron microscope. Technically, mathematically, what I'm actually doing is I'm calculating the center of mass of each diffraction pattern. So if you think about it, as you're scanning your image, what you do is you get an electron diffraction pattern from each position. So at each diffraction pattern gives you the center of mass, or the expectation value of momentum. And mathematically, what I'm doing is I'm applying this equation to get back my magnetic field. So this visual is just showing that how the magnetic field can change, or from one position to another position because of the deflection. It's just a visual. But mathematically, I'm utilizing this Ehrenfest theorem.
How do you
Oh, so,
how do you calculate the E part?
oh, so I'm ignoring the E part because what happens is that if you look at this slide here, what you see is that there is actually, so what you can, so there's two ways to do that. So the electric field give you the gradient of your potential, whereas the magnetic field is the curl of your potential. So you can separate it from the gradient of potential. So it gets a little bit complicated, but what you can assume is that because magnetic field deflections are quite small, so then they're on the order of tens of microradians, whereas your electric field deflections are on the orders of milliradians. If you make your, if you change your experimental parameters, where you see how the scale bar is 100 microradians. So if your magnetic field is only going to shift on the order of 10 microradians, your electric field is going to shift way more than that. So it's going to take your center of mass image off the board. And so because the shifts are so different, you can actually separate them in experiments.
Thank you.
Yeah.
I have another question.
Sure. And so, sorry, but, and then that's how you can able to look at, for example, fermions without worrying about the local electric field. But they do come up, but there's other ways to separate them experimentally. Yeah.
Riyad, you had a second question. Are you here? Can you hear me? Okay, we'll circle back to him again. So there is a question in the chat box. It's from Pritham. He says that really fascinating talk. Thanks for that. I just wanted to know whether these magnetic vortices are static, stable in time at finite temperature, and what is generally the temperature for such experiments?
Yes, so I do have the temperature for this one. So this is at 100 Kelvin, so nitrogen temperature, and we're applying a field of 111 millitesla using our objective lens. So we're turning on the field a little bit to get them. So I would say that they're pretty stable at liquid nitrogen temperature and with applied field, like they don't change. But you can also do, for example, in situ Lorentz microscopy, where you can change the magnetic field or you can change the temperature, and these magnetic vortices would go away. But in our experiment, we find that they're pretty stable at liquid nitrogen and at a field of 100 millitesla.
Okay, Riyaj, are you here? Can you? So Pritham says, awesome, thank you. Thank you so much, Pritham, for asking the question. So Riyaj, if you are able to hear me, can you ask your second question? Okay, I will ask one question.
Yeah.
You know, in these electron microscopy imaging, like you guys are seeing more than anyone else. Like you really, really high resolution, sometimes like below 1 angstrom or close to 1 angstrom. You can have all these beautiful images, but it's like a general question, you know, if it's at all possible, because you are seeing things in projection, right?
Yeah.
So, you know, when you're trying to do a 3D mapping, now you have to do in two different directions. Like you have to rotate the sample physically and then have these 3D information, right? So do you think, is it ever possible to get to the point that where we can just have the sample and, you know, have like all 3D informations, even 4D, like in case maybe?
Yeah, no, that's a great question. Thank you for asking, Sharia. I think that the answer is yes, there is a technique out there. There was a recent paper in Science that was that came out in 2021. It's called multi-slice typography. So what they're doing in that technique is that they're taking the electron beam and diffraction pattern projection, and they're what they're doing is they're modeling the probe as it changes through a three-dimensional structure. And so they can get back this the atomic slices at each thickness of your sample. And so you can see that the atoms in your sample are actually vibrating depending on what kind of thickness within the crystal that you're looking at. So that's one way they're doing it. And it's actually a really groundbreaking technique, because now we can solve so many problems that we want in 3-dimensional just by looking at our projection of our diffraction pattern. The second way that people typically have been looking for 3-dimensional structure is by looking at tomographs or using electron tomography, where they take their sample and they rotate it 360 degrees. There is like a missing wedge because your sample holder, your sample holder is like this, and your sample is in the middle, and so there are some angles that you can't really look at because your holder is going to get in the way. So you can do this sort of tomographs. But yeah, there's two techniques that I think are really cool. The first is multi-slice typography, and the second is electron tomography. And I think that, like, for people in the field of cryo-EM, so cryo-electron microscopy, to look at biological structures, what they do is they take TM images of like biomolecules and they just kind of like make a ton of biomolecules, like literally a ton, take a bunch of TM images, and through computation techniques, they can reconstruct these biomolecules in 3 dimensions. And that technique actually won the Nobel Prize in 2017. So yeah.
Awesome. I sometimes wonder, like, what's the next step then? And this, I'm not sure how to do that, but yeah, it's a great answer. And I think people are making really, really good progress in there, and probably will be able to see like even more progress in that regard. So related to that, and then if you think that, if we can see these 3D structures, then for some of the ferroelectric or ferromagnetic materials, they don't just have polarization in the px and py direction. Sometimes they also have pz direction. So do you think that we'll be able to see those like 3D polarization as well?
Yeah, so with multi-slice typography, what you can do is, because you can look at changes in atomic structure at different thicknesses of your sample. So in that science paper, what they showed is that you can look at praseodymium scandate. You can see that in different thickness of your sample, you have different dopants. So it's a dope crystal with where you can look at and locate the dopants in this 3-dimensional projection. Now, what their experimental conditions are is they're using a beam that is quite small, but their convergence angle that they're using is about 22 milliradians. So a 22 milliradian convergence angle only gives you a depth resolution of about 4 nanometers. So their sample is about 20 nanometers, and so they have this depth resolution of 4 nanometers. For polarization, what you need is angstrom scale resolution to look at the shifts in polarization, the shifts in displacement in the z direction or in the z direction. And so what you can do experimentally is that instead of using a 22 milliradian convergence angle, you open up that convergence angle up to something about 70 milliradians. And then now you have a depth resolution of about 6 angstroms. And that is how you're going to be able to do and look at polarization in the z direction. No one has done it before, but it's possible.
Yep. That would be helpful for my project as well,
Yeah, for sure.
So is there anyone else who wants to ask any more question? Yeah, I think we went through the questions in the chat, and I know that one person had a second question, but I think we kind of lost him. He's not in the Zoom meeting anymore. Well, I think if there is no further question, then I'd like to thank once again. Thank you so much, Kayla, for joining us and for giving this wonderful talk. And I'd also like to thank all the members who joined this talk. It was a really interesting experience for me, as at least hearing from you, these beautiful techniques and all these, emergent things that you are doing. I think it's a great learning opportunity for me. So once again, thank you so much. And I think we can kind of end here. If you have anything to say, Kayla.
Yeah, thank you for inviting me. This is a really great opportunity to connect with students from overseas and Sharia's alma mater. So thank you so much for inviting me.
Yep. And yeah, I mean, it's such inspiration to hear from someone like you. And, a lot of these students, I mean, I was there, when I was in my undergrad. So I know that it's a very inspiring opportunity, and it's always great to see at least where the field is growing from, various postdocs or PhD students. And I think it's a very good learning opportunity, and they actually I'm sure they enjoyed a lot about like hearing from you. So yeah,
Great.
thank you so much. And this group MMMRN, it's from my alma mater, so it's a multi-skill mechanical modeling and research network. It's mostly mechanical students, but we're doing few material science, and from like even after doing undergrad from mechanical, people are going to material science. So it's kind of related. So so MMMRN, this is giving these students a unique opportunity. There's not so many research groups that are really active in Bangladesh, I'm not gonna lie, but there are a few, and I think one of them is MMMRN. It's doing very great. So it's just getting the exposure to the scientists and to the leaders of the field. I think that was kind of important, and that's where we're trying to aim for. So yeah, it's an amazing opportunity. Yeah.
Yeah, great. So actually, I had way more equations. I actually try to make my talk like more visual and less equation based, because there's a lot of technique and math that comes into it. Like I have like 20 pages of math in my paper, but I thought I changed it for this talk actually. Yeah.
Oh, thank you so much. Yeah, I knew. I mean, it's your talk is heavily physics based, and you're from physics background, so that's totally understandable. But I think the visuals actually helped, at least for me. I mean, if it was just math, it would be really
Yeah,
difficult.
it's super boring, I know.
It's not boring, but it's just, it takes some time to really grasp the idea, and sometimes you just miss it, and then the rest of the talk you just don't understand that much. Yeah, so again, I think thanks from the MMRN as well.
Okay.
Yeah,
Okay. All right.
bye
Well,
bye. Yeah.
all right. Bye.